All right, so the next example we're going to do is a little bit more complicated. I want to show you one of those 3x3 cases. So we're going to do it for your spherical coordinates. So real quick, let me pull those up. Should have done it while I was breaking between the videos. X is going to be rho cosine theta sine phi. Y then is rho sine theta sine phi, and z is going to be rho cosine phi. And we're going to try to find that rho squared sine phi that we know shows up when we write the dv for these spherical coordinates. To do that, I'm going to have to take all my partial derivatives and then a 3x3 determinant. So this is going to be kind of a long problem. But I'm going to just start by plugging through my derivatives. Dx d rho is going to be cosine theta sine phi. Dx d theta is going to be derivative cosine makes a minus, minus sine theta sine phi. And derivative of x with respect to phi is going to be rho cosine theta cosine phi. And remember, when we take these partial derivatives, we just sort of ignore every variable that we're not taking the derivative of at that time, treat it like a constant. It starts to look more intimidating when we have all these trig functions and when we have 3 variables compared to that first very easy case where it was like all numbers and there were only 2 of them. But just be careful. Really silly derivative mistakes are what will get you in this section more than anything else. And then we're going to try to do y next. It's going to be very similar. dy d rho just gives us our sine theta sine phi. dy d theta gives us, sine is fine, rho cosine theta sine phi, and dy d phi, sine is still fine, rho sine theta cosine phi. Okay, and then finally z. This one's going to be easier because there's no theta in it. So dz d rho is just going to give us our cosine phi. Then dz d theta, because there is no theta, its derivative is 0. So it's like the derivative of 1 with respect to x is 0. Derivative of rho cosine phi, because there's no theta, is 0. And then dz d phi is going to be cosine switches minus rho sine phi. And then we're going to put this all into our Jacobian. Normally I do that dx d rho, dx d theta, dx d phi. I'll just do it. It's just going to be so messy. Dx d rho, dx d theta, dx d phi. So I do x in my top row, and then I move across and do the different derivatives. Then I do y next, dy d rho, dy d theta, dy d phi, and then z, dz d rho, dz d theta, dz d phi. Okay. Or for the variables and derivatives that I just calculated, it's going to be cosine theta sine phi minus rho sine theta sine phi, rho cosine theta cosine phi. For all my x derivatives, I just pulled these 3 and put them in the top row. Then my y derivatives, sine theta sine phi, rho cosine theta sine phi, and rho sine theta cosine phi. And then for z, dz d rho was cosine phi. I got this nice 0 in the middle. And then dz d phi was that minus rho sine phi. And at this point, we've populated the Jacobian. So we took all the derivatives, we put them in the special shape they're supposed to have, and then to finish the problem, I have to take the determinant of this 3 by 3 matrix. And here's the part where we kind of have to stop and talk about how you take a determinant for a 3 by 3 matrix, if you're not already familiar with it. Our approach is going to be, because we know how to take a determinant for a 2 by 2, we're going to sort of break it up into a bunch of 2 by 2 determinants that we add together. The way we do that is we're going to pick an entry. So if I picked that one, then I'm going to ignore everything that's in the same row or column as that entry, and I'm going to take the determinant of what's left over. And then I'm going to repeat that until I've traveled along an entire row or column. So then if I was going along, I could do this one next, ignore all those entries, and take determinant of the 4 that are left over. 2 tricks to this. One, when we add all the determinants we take together, we actually alternate signs. So I'll take this one, then I'll subtract this one, then I'll add this one. But also, I get to pick which row or column I choose to work on. And so generally, if I see a 0, I want to make sure to include that row or column in my calculation, because then there's a whole determinant I get to skip. So to reach whatever row or column you want to do, just remember that you always have a plus in the upper left, and then change by sign however you need to. So if I start with plus, then moving down I would do minus, and then moving down again I would get back to plus. And then if I move left to right from there, I have my plus, minus, plus. So what I want to do is calculate my determinants along this row. That way I get to go through the 0. And now I know the sign that I use to multiply my different subdeterminants I calculate. So what this is going to look like, so that you all have it on one screen, I think I'm going to copy paste this. You don't have to rewrite it. Presumably your paper is all in a row, or you can flip back and forth when you want to. Okay, so there's the thing we were just looking at. I'm going to delete it when we're done with this. So I'm just putting it right there. But for this determinant process, I'm going to start with that cosine phi entry. It's a plus. And then I'm going to ignore everything that's in the same column or row, and I'll take a determinant of what's left over. My minus rho sine theta sine phi, rho cosine theta cosine phi, rho cosine theta sine phi, and rho sine theta cosine phi. That's just these 4 entries is what I chose to write down just now. Okay, I'm going to erase these extra pluses and minuses I didn't use. Then after I write that down, I would just continue along the row that I picked. So next I'm going to choose 0, and I would cross out everything in the same row and everything in the same column, and I would do minus 0. I'm sure that'll come back in a second. Minus 0 times the determinant of what's left over. This isn't going to matter because it's multiplied by 0, but I'm going to write it out just so that you can see the process, because some of us are still learning what a determinant is. So I would do cosine theta sine phi, rho cosine theta cosine phi, sine theta sine phi, and rho sine theta cosine phi. For a second, I almost included this minus sign. So just be careful if you're like me, a little bit forgetful when you're doing things. Make sure that the marks you make for what sign to keep, you don't accidentally add to your determinant. Okay, and then my last entry is going to be this row sine phi. So I ignore everything that's in the same row or column, and I add that one. And then I do the entries that are left over. Cosine theta sine phi minus rho sine theta sine phi, sine theta sine phi, rho cosine theta sine phi. Okay. And now that I've written all this down, I'm going to just go ahead and erase that whole old determinant that I had put on the page for us. And at this point, I've broken down that 3 by 3 into 3 2 by 2s that I can just use the normal like cross multiply minus process, or if that process is like hard for you to remember, you can also have remember just that it's like this times this minus this times this. That's fine too. So I'm going to get cosine phi times minus rho squared, because I'll have rho times rho, sine squared theta, sine phi, cosine theta, phi. Lots of angles here. Okay, so let me make sure I did that multiply right. Rho times rho gave me rho squared. Sine times sine gave me sine squared. Then I have sine phi, cosine phi. Cool. And then I subtract, multiplying the other direction. So I'm going to have rho times rho gives me rho squared. Cosine times cosine gives me cosine squared. And then I again have that cosine phi, sine phi. For my second determinant, I'm not going to do that one because it's multiplied by 0, but we would do that same multiply minus multiply. Hopefully you're going to see enough practice with the other two though to be kind of comfortable with that. And then for my last determinant, I have rho sine phi times, and I multiply along the main diagonal. I have rho times 1, so just rho. Then cosine times cosine gives me cosine squared theta. Sine times sine gives me sine squared phi. Then minus, and I have minus rho times 1, so just rho. Then sine times sine is sine squared theta times sine squared phi. And now I've taken all the determinants. So at this point, it is only an algebra problem. I need to simplify this because someday I will put it inside an integral, and it's really messy the way it is now. I would not want to integrate it. So I'm going to start by just distributing everything. Let's see what we end up with at that point. So I've got minus rho squared sine squared theta sine phi cosine squared phi minus rho squared cosine squared theta cosine squared phi sine phi. Plus rho squared cosine squared theta sine squared phi sine phi. I'm not multiplying that to be a sine cubed phi because sine cubed like never makes my life easier. Squared does, so I want to see all the squared that I can. But if I turn this into a cubed, I might miss when I'm able to do a cosine squared plus sine squared, and I quite like those. Then this minus minus becomes plus. So I've got plus rho squared sine squared theta sine squared phi sine phi. All right. I'm getting kind of close to the bottom of this page, so I'm going to go ahead and copy paste it to the next. And I will just leave it there so that we can see it. And then let's start pulling out all the like terms that I can. So I've got a rho squared in every term. So I'm going to pull that out. I've also got a sine phi in every term. So I'll pull that out. And then so I can see that there's like no single term that's the same between all of them at this point. Or I can see that rho squared sine phi is the answer I want to have. So presumably the rest of this is going to cancel out somehow. So then inside I've got my minus sine squared theta cosine squared phi minus cosine squared theta cosine squared phi plus cosine squared theta sine squared phi plus sine squared theta sine squared phi. All right. And then for my top two terms, I see a sine squared and a cosine squared of the same angle. And then what's left over is the same. So I'm going to pull out that comma minus cosine squared phi times sine squared theta plus cosine squared theta. And I see the same here. Cosine squared theta, sine squared theta, with the common sine squared phi outside. Okay, so then I've got my rho squared sine phi, and then my sine squared plus cosine squared in both cases just becomes 1. So I'm left with sine squared phi minus cosine squared phi. And that would be my d of x, y, z over d of rho theta phi. So that's good. And then lastly, we just want to find that dv thing. Where we take dx, dy, oh no, dz into, it should be rho squared sine phi, but let's say we don't know, to whatever d rho, d theta, d phi. And then at this point, all we have to do is take the absolute value of what we found already. Area and volume are like positive things, so it's possible for a negative to come out of a determinant, but it shouldn't in this context. So absolute value rho squared sine phi sine squared phi minus cosine squared phi is the same as just getting rid of all your minuses. So it's rho squared sine phi sine squared phi plus rho squared sine phi cosine squared phi. And then at this point, we have a sine squared, cosine squared that are going to cancel out. We'll end up at rho squared sine phi times, was it the sine or cosine I wrote first? Sine. Sine squared phi plus cosine squared phi is equal to rho squared sine phi. So I would know that dy dx dz is equal to rho squared sine phi d rho d theta d phi. And I'm done. Doing a 3x3 and showing that the spherical formula is like what we thought it was. I think I did the same thing to you all here without explaining why I was doing it. That derivative was negative, but the quantity I put into my dA is positive. So maybe somewhere in your notes I should be here. Let's just make sure to put that absolute value bar there. That way you know that the answer you put into the integral should be positive. But if you're just asked to calculate that thing, it can be negative. And that's it for the 3x3 example. Next up, I'm just going to do one where we're like reversing the change of variables, just because you might be curious about that.